welcome back. In today's discussion, I am going to tackle the idea of subspace. Okay, and again, I am assuming that you know the definition of subspace, but in today's lecture, I am going to just explore that what is need of the subspace whenever you are going to discuss about the control problems, okay, or system engineering problems. So I am going to devise the definition, and after that I am going to proceed towards its application. So if you remember the previous class, I have talked about the vectors, and I have told you that vectors may be some kind of column vectors, some kind of matrices, or some kind of functions too. Okay, so now we have, whenever we are talking about the vectors, at that time I don't have any restriction that I have just a column vectors. After that, we have seen that if I know how to add numbers, then how to extend same kind of concept to add to matrices, to functions, and after that I have told you that how basically that become very useful in order to develop some kind of machine based on minimum number of hardware. Okay, in today's lecture I am going to discuss the subspace, and if you see the subspace, what is main motivation that inside the vector space it is possible to show that there exists some set of vector which will satisfy the all property of the vector space. Okay, so what I mean to say, suppose if you take the three-dimensional space, and if you consider some kind of plane which is passing through the origin, and since I am talking about the plane, so plane in three-dimensional space, that is represented by two dimension. Okay, so but since I am considering this plane in three-dimensional plane, so I cannot tell that this represent two dimension. Okay, because always third component associated with this particular plane R2, that is 0. Okay, and it is possible to show that if I take any two line in this particular plane, then addition of that line remains inside this plane only. You can take any two line in this plane, and it is possible to show their addition inside this plane only. Even if you can scale it out, it is possible to show that we are going to live inside the same plane. Okay, so this particular plane inside this three-dimensional plane which passed through the origin has same property like vector space. Okay, and due to that reason we are going to identify this subset of vector as a subspace. So that is the main motivation. It means that inside the vector space, and vector space may be any form, there exists some subset of vectors which is going to contain all property of the vector space. Okay, and that I am going to identify as a subspace. Okay, so in order to define the subspace, I need one further definition, that is called definition of linear combination. Okay, so it is possible to show that if I know this definition, so using help of this definition I can able to define the notion of subspace. Okay, so what I am going to assume, I am going to assume that I have some kind of vector space V, and in the previous class we have seen that whenever we are going to define some kind of vector space, then I need some notion of element that is called field, or I need some kind of a scalar. Based on that, I can define the vector addition and scalar multiplication, two binary operations. So, and we are going to make sure that some axioms will satisfy. So what I am assuming here, in order to define the linear combination, I have some kind of vector space, means I have vectors. I am not caring that what kind of vectors now I have, any combination of column vectors or matrices or function I am going to consider. And after that, what I am going to tell, suppose I have alpha 1, alpha 2 and alpha n are the elements of these vectors. Okay, so in this space I have element like alpha 1, alpha 2 and alpha n, and what I am going to do, I have to represent some vector alpha in the same space. It is possible to show that if I select some a1, a2, an, that is a scalar from this field, and if I am going to write like this, then I can tell that this vector alpha is the linear combination of all other vector alpha 1, alpha 2 and alpha n. Okay, and this concept is basically very important, because for example, if I take two-dimensional space, so in this two-dimensional space, I have infinite many vectors. Okay, so it is difficult to tell or identify all vectors inside the space. Okay, so what is basic motivation? That I will try to identify minimal number of vector, and using that I try to span the whole space. Okay, and it is possible to show that if I select some vector like 1 0 and 0 1, then scaling this vector by some proper scalar I am going to define same like definition a1 you can select, or x you can select, and y, then it is possible to show that any point in this space I can represent the linear combination of these two vectors, and that two vectors in the next class I am going to give some name, and that name is basis. Okay, so you, based on these two vectors, I can able to span anywhere inside this space. Okay, and this is nothing but the linear combination. Okay, xy is the linear combination of these two vector 1 0 and 0 1. Okay, so now there is no need to worry about the each and every vector. Okay, if you have to reach anywhere, just you have to do a scaling. Okay, so linear combination here provide us broader picture such that I can represent any vector inside the space. Okay, so let us try to see some example. Suppose 2 1, a linear combination of 1 1 and 1 2 in R2. So I have to check that if I have some kind of vector like this, and in place of 1 0 and 0 1, if now I am going to select these two vectors, then is it possible to represent 2 1 using these two vectors? So for that I have to make sure that linear combination of these two vectors where two scalars comes into picture, and here a scalar, if you see, since I am going to talk about the space R2 space, and each entry I have represented as a row vector or column vector, that doesn't matter for us. So in form of row vector I have represented, but you can represent by column vector. This is the transpose. Okay, so now what I am going to do, I am going to check that using these two vectors, same like here 1 0 and 0, is it possible to represent this? Okay, so just I have to make sure that there exist two scalars from the same field, and here whenever I have constructed this vector, at that time I have used the real numbers. Okay, so if I am able to get two real numbers, then I will tell that yes, it is possible to represent 2 1 using 1 1 and 1 2. Okay, similarly, suppose if I have 0 1, so similar kind of things I can able to do. So now more generally, which vector in R2 are the linear combination of 1 1 and 1 2. Okay, so that I am going to check, and it is possible to show. During school time we have done this kind of calculation basically. So what I have to do, since I am telling that which kind of vector in this two-dimensional space that is represented by these two vectors 1 1 and 1 2, and due to that reason now I have to find this set of the scalars such that these equations comes into picture. So that kind of things I have to search for. Okay, and due to that reason I am going to solve this equation, and if you solve this equation it is possible to show that there exists a eta and zeta like this, such that I can able to generate any vector alpha and beta. Okay, so what is our conclusion? That if you take any vectors, okay, that can be represented using these two vectors. You can also able to write in form of column vectors. So now you can see that using these two vectors also I can able to span in whole space, not only 0 1 or 1 0, these two vectors. I have another set of vectors, using that I can able to span the whole space. Okay, so it is possible to show there exist infinite many combination such that using that particular minimum number of vector I can able to span the whole space. Okay, and this concept is very useful. Okay, in later part of this lecture I will tell you that that concept gives us the idea of how to select the coordinate frame for some system. Okay, this is also motivate us that if you are in some space, then there exist infinite many combination or infinite many way to represent this space. Okay, so due to that reason idea of linear combination is very important. Okay, now let us come to the our main goal. So main goal of today's lecture is to talk about the subspace. Okay, so I am going to start with the vector space, and after that I will come to the subspace. So in the previous class what we have seen, that whenever we are talking about the vector space, then at that time I have to check 4 different axioms. Okay, so I am categorizing the axioms in form of set, due to that reason 4, but if you see carefully then that is total 10 axioms. So I need vectors. I have already told you that may be in column form, row form, or functions in form of matrices, and after that I have to select the scalar, and after that I have to make sure that vector and scalar distributive law that will satisfy, associative law satisfy, and a scalar identity will satisfy. Okay, so I have categorized whole 10 law in set of these 4, and after that I am telling that all are independent. Okay, so please be careful whenever we are defining something, and if I have to check more than one axioms, then equally I have to show that all axioms are independent. Okay, if one axioms can imply other, then that definition is improper definition. Okay, so whatever property we are telling to check that if these two property will satisfy, then some notion comes into picture. So when I have started this course, at that time I have talked about the superposition. Okay, if you remember, then in superposition principle what I have told, that I have to check 2 things, that is additivity, and second thing, that is homogeneity. So what does it mean? That these two axioms should be independent. It means that this should not happen, either this should not happen always. At least I have to tell that one situation this will violate it. Okay, therefore a vector space is a abelian group. We have already understood that what is meaning of abelian group. Okay, so whenever we are talking about group, then I have some way to operate to do one operation, one binary operation, and I have to check the 5 axioms that going to satisfy. Okay, now on which f acts so that 4 independent axioms are satisfied. So in that way also I can define the vector space. Okay, so let us try to see some example and counter examples of the vector space. Whenever you are trying to understand something, then you have to also select some kind of counter example. Then you are able to, counter example means I have taken some kind of definition. Okay, so we have to show that whatever property I have stated that is satisfied by this group, and I have to also find out where this definition is not valid. Okay, so here you can see that the set P is polynomial of all polynomial with real coefficient. So I am going to talk about the polynomial where degree, so that subset P3 of polynomial is less than equal to 3. Okay, so P3 I am going to define like something A1 alpha 1 x cube, A2 alpha 1 x squared, something like that, less than equal to 0. Okay, and it is possible to show that if you talk about component wise addition and again this multiplication means component wise addition, then all property will satisfy, all property of vector space will satisfy. Okay, so less than equal to 3, then that will satisfy the vector space. But if you just tell strictly 3, then it might possible that will not satisfy. Okay, and it is possible to show some kind of counter example. What you can do, you can create another polynomial and just you can put a1 alpha 1 cube with negative sign, and after that what happens that if you add it, then the overall degree that is less than that become 2. So if you are just talking polynomial and if polynomial degree is strictly 3, then that will not form a vector space. Okay, because after addition we come to the different space that is P2. Okay, and due to that reason I cannot give guarantee that we are going to live in same space. But if I put less than equal to 3, it means that all polynomial of degree 3, 2, 1, 0, everything is included. Now let us try to see some another example. The subset Q3 of R3 means R3 I have some kind of real number 3-dimensional space where each entry is real number. Now what I am going to do, I am going to consider some kind of triplet x, y, z you can take, that is nothing but rational coordinate. Okay, so x is rational, y is rational and z is rational. Okay, and what I am going to do, this coordinate I am going to select in R3. So obviously my scalar or f is nothing but real number. Okay, so real number might contain some kind of irrational quantity also, rational as well as irrational, and if you multiply rational quantity with irrational quantity, means a scalar multiplication, that will not satisfy, that will give you the irrational quantity, and due to that reason I can tell that this subset Q3 of R3 not form a vector space. Okay, but you can see that polynomial of n you can take nth degree less than equal to n, and if you consider polynomial less than equal to 3, then that will give us the same property like vector space. Okay, similarly if you can take some kind of subset of R3 consisting of all triplet with at least one coordinate equal to 0, then that will not form a vector space. Okay, because it might possible if we are just telling at least one coordinate, so I can able to define like this and 1 0 0. Okay, and if you do addition, then at that time what happens, all three coordinate become non-zero. Okay, and due to that reason this subset which contain all triplet at least one coordinate equal to 0 is not a vector space. Okay, so I have given some example, some mathematical example, and if you see carefully, then this kind of mathematical equation or expression that is frequently coming during our analysis whenever we are designing the machine. So you have to become very careful. Okay, Now let us come to the definition. Okay, so from the previous example, what we have seen that R3 itself a vector space, and after that what we have seen that there exists some kind of subset inside this particular space that will also satisfy the property like vector space, this two-dimensional plane. So what I am telling that three-dimensional space, a plane that passed through origin is a subspace as the line passing through the origin. We will check that why I am telling that only line passing through origin. Okay, so if line passing through origin, it is possible to show that if you take any two vectors that remains in the same space, and if after during the Bendy operation like addition, or if you scale out, that is going to remain in the same space. Okay, so due to that reason, I have some kind of vector. So what kind of vector this is? I have two quantity that is known 0 and one quantity I have 0, and it is possible to show that this particular quantity going to represent some kind of subspace, some kind of vector space like property. Due to that reason, I need some extra definition to quantify these kind of those kind of vector which has similar property, or which has similar property like vector space. Okay, so definition is like that: a non-empty subset M of a vector V. So suppose I have big picture, and in this big picture, if I will consider these many of vectors, then that will form a vector space. Now I am going to see the smaller picture inside that. Okay, and if we are able to give guarantee that sum of two vectors in M always remains in M. It means that I have to make sure that if I operate the vector addition, so that will not leave this space. And if product of a vector with every scalar is always inside M, then I can tell that that particular subset M of this vector space V is subspace. Okay, so idea is very simple, that when I have started this course, at that time I have talked about this set. Okay, now inside this set is nothing but some unordered collection, and suppose that I have collection of 20 objects, and after that I have pick up 5 objects, so that is subset. Now what I am going to do, similar kind of things I am going to perform on vector space. Okay, so what I am going to do, suppose I have some kind of set with two boundary operation, and if they will satisfy certain axioms, now I am going to select some part and try to show that similar property is going to satisfy. If the similar property means if you add two vectors, then from this subset, and if whatever result that comes into picture that again live in this space, then I will tell that this is nothing but some kind of subspace of this original vector space V. Okay, now either you can check this definition, or directly using linear combination you can give the another definition. So due to that reason I have written here equivalent definition. So a non-empty subset M of a vector space is called a subspace V if every vector of form alpha x and beta y in M, whenever x and y both are in V and alpha beta are arbitrary scalar. What I mean to say, that I have this space M. Now I can take two vectors x and y, and after that, since I have to also check that product of vector with the scalar that is going to remain in this space, and due to that reason I have applied the scaling, and a scaling of alpha and beta I have applied, and after that I have shown that after doing this scaling I am in here. So either you can check this definition or this definition. So most of time equivalent definition, whenever I have situation comes into picture, then that is very easy to apply the equivalent definition to check something. Okay, due to that reason, whenever some numerical problem or some realistic problem comes into picture, then there is no need to check that combination of two vectors inside this and after that scalar multiplication. Just you can check this, that linear combination of two vectors x and y, that is going to lie inside M. So that is enough to tell us that if alpha x plus beta y belongs to M, and it is possible to show that whenever we are checking this, then automatically we are giving guarantee that origin is also belongs to same set, then that will form the subspace. Okay, so entire space X itself a subspace. That is obvious, because I am telling, I have defined that some kind of vectors, so some subset of vectors that has same property like the vectors. Now I have taken the whole space, so obviously that is also a subspace. So whenever we are talking about proper subspace, it means that I am not going to include all vectors of the space. Okay, now let us see that what is special about the origin. Okay, so whenever I am talking about origin, so please be careful. Origin may be depending on that what kind of vectors I have selected and what kind of scalars or field element I have selected in order to develop the vector space. Okay, because if you are just talking about the column vectors, at that time my origin is represented like this, and if you are changing the space, at that time it might possible, suppose I have matrix, at that time I have to define origin in different way, similarly for the functions. Okay, so what is special about the origin? It is necessarily belongs to the every space. And why that is so? Because M is a subspace and X is any arbitrary element of M, then 0x belongs to M. Okay, because what I have to do, I have to make sure that whatever field element, so if I multiply field element with vectors, then that remains inside the vector. So obviously one field element, because in order to satisfy the definition of field, we know that always origin comes into picture, and if I multiply 0 or origin to V, then that will produce some kind of vector, that is 0 vector, and due to that reason, in order to fulfill that, origin should always inside the subspace. Okay, so the definition of subspace could have been formulated in this way. Another way, a subset M of a vector space V if M itself a vector space with respect to the same operation. Okay, so it means that I have very large space, inside that I have a smaller space, and that will satisfy the all property of the bigger space. That is the meaning. And most of time whenever we are performing application, at that time our requirement is not whole space, always our requirement is a smaller. Let us let us try to see one example. Suppose that something is rotating. Okay, at that time it is possible to represent that theta dot equal to omega and omega dot equal to some controlling function. Okay, so this is angle and this is angular velocity. Okay, now this will form two-dimensional space because theta and omega, two coordinate is required. If you see the physical situation, so in most physical situation, what happens? This angle that is going to lie from minus pi to pi, and omega, I have some quantity that is going to lie in pi to pi, but it might possible their derivative may be anything, and due to that reason, whatever space that comes into picture, that is this space only. Okay, I am not going to consider the whole space. Okay, now I have to make sure whenever we are going to design this kind of control action, at that time we have to make sure that I am not going to leave this space. Otherwise if I will give some command to the system, then system is not able to understand the command, because they know that all quantity, whatever that is going to become responsible for the theta and omega, that should belongs in this space. Okay, so I have to define operation in very proper way, such that after defining the operation I can able to live in this space. And due to that reason, most of time in practical situation, the notion of subspace comes into picture. Okay, now let us see some kind of numerical example of subspace, and after that I will come to the physical example. Okay, so what I have done, I have generated some kind of vector space with help of the functions. So here inside the space, each element is nothing but some kind of function, and what I am telling, that field is nothing but real number. And after that I am also considering that whatever vector space that is belongs to R, one dimensional vector space only. Okay, so this vector space basically mapping from real to real. Okay, so really a real valued function I have just. Okay, so each entry of this vector space where v1 belongs to v, okay, that is nothing but mapping from real number to real number. Okay, now what I have to do, I have defined some kind of expression, and after that I am going to check that that particular expression is going to form some kind of subspace or not. Okay, so I have fx square equal to fx square f0 f1 f3 1 plus f minus 5, and I am going to show you that all operations whatever I have defined here. Okay, so somehow I am constraining my element that should follow this kind of relationship. Okay, and it is possible to show that sometime it will consistent with respect to vector space, sometime it lose their property. Okay, so let us try to check the first example. So what I have done, I am telling that okay, I have some kind of vector space v. Okay, and inside that I have some kind of element, so v1 that belongs to this v, and what I am assuming that v1 map from R to R. Now inside that I have defined some kind of a space w, and w function here f that belongs to vector v, and they will satisfy this kind of property. Okay, it means that whatever f I am going to select, that I am going to select with this vector space. Okay, and after that, after equating with this kind of expression, I am telling that whatever quantity that is generated, that is the subset of this whole space V. Okay, now I have to check that W is subspace of V or not. Okay, so I have already told you that something is subspace, then just you can select two vectors, two general vector F and G that belongs to W, and after that here I am assuming that field element is nothing but real number. So you can take two element from the field A and B, and after that you can define the linear combination. So in place of F, now you can write AF plus BG. Okay, and after that what I am going to do, I am going to open it and try to check that left hand side equal to right hand side or not. Any confusion? And it is possible to show that that is not satisfied. Okay, so due to that reason, if you define like this, then this will not form a subspace. Now let us come to the second example, where I have now changed the operation like f0 equal to f1. Okay, again I have defined in the same way. I have defined a space w where f is coming from vector space, and that will satisfy this kind of relationship. And again I have generated AF plus BG, and it is possible to show that actually equality relation will satisfy, and due to that reason W is the subspace of vector space B. So if I define some kind of relationship, so I have whole space, I don't know the relationship, I just know how to add two vectors, how to scale out two vectors, and here if I define some kind of operation, then now I am going to see that after defining this kind of particular operation, this consistent with vector space or not. Okay, and what we found that okay, this relationship is valid. Now let us again change it, f3 equal to 1 plus f minus 5, and it is possible to show now this relationship will not satisfy. It is very easy to check, due to that reason I am not checking. Okay, so please do by yourself. Now let us come to the next one, that I have written f minus 1 equal to 0. Okay, and if again you can generate the space, and after that just check that this space will satisfy this kind of property, that all element like af plus bg, that is going to lie on same space or not after performing this operation, and it is possible to show that again this will valid. It means that if I have some kind of real valued function which is mapping from field R to R, and if I define operation like this, then that will form a subspace. Now all f which are continuous. Okay, so now what I am going to do, I have taken only continuous function from the real valued space. So I have some kind of vectors which map from R to R, and out of this I have, it might possible I have continuous function, discontinuous function. Out of that, what I have done, now I am going to consider those kind of a space. So this space which is just give the mapping, and after that a smaller space where I am just going to consider the continuous function. Okay, again I will define what is meaning of continuity. But during school time we have learned that if left hand side, left hand limit, right hand limit, and limit at that point that is equal in one dimensional plane, then whatever function, whatever quantity I am going to consider, that is continuous. So same definition I have used here. So it is possible to show that if f and g are continuous function, so af plus bg is also continuous function. Okay, and due to that reason, suppose if I have some kind of vector space which is generated over the real number, and if that map to some kind of real number, then, and if that is continuous function, then that particular subset will form the vector space. And this kind of idea we are using a lot of time during our analysis. You can, if you see carefully, whatever dynamical system I am assuming, here I am assuming that x dot exists. It means that I am assuming x is continuous. Okay, so always I am going to consider some kind of continuous function, and here you can just restrict yourself x belongs to R. And if you see the solution of this particular x0 and 0 to t and fx tau d tau, something like that. Okay, so it is possible to show that if you just consider xt which will continuous. Okay, so it means that whenever I am writing this, then at that time I am assuming those kind of a space where a state variable is continuous function. I am not going to consider those kind of a state which is discontinuous whenever I am writing this kind of equation, differential equation during the mathematical modeling. So that kind of inherent assumption I have. Okay, now let us come to the some more example. Okay, and most of time during from the school time onward we are solving ax equal to 0. This kind of equation we are solving, and it is possible to show that solution, if that is exist, then that will form the vector space. Okay, so I have here I haven't considered the Rn. Here you can consider any field. Okay, and it is possible to show that solution, if solution exists, then that will form the subspace. But if you will take ax equal to b, then obviously I cannot able to show that origin exists or origin will satisfy this, because x equal to 0, then that will not satisfy. And what we have seen that origin should always exist in that space. Due to that reason, this will not form a vector space if I am trying to solve ax equal to b. So next part of this course I will tell you that how to solve it. Okay, and how to correlate this with the notion of vector space. Okay, if you write differential equation, okay, most of time during mathematical modeling I have some kind of autonomous system, and this is linear time invariant system. Okay, so what is meaning of linear time invariant autonomous system? We are talking about this kind of system, x dot equal to ax. Okay, that might be any order, x belongs to Rn. Okay, so here this is second order differential equation, very special case of this equation, and it is possible to show that again w, because I am equating with 0, that will form the subspace. Okay, and it is pretty easy. You can just change y1 and y2 like this, and after that check this will satisfy this. Okay, so if a vector space V is the set of all real valued continuous function over the field of real number, then set W of differential equation. Okay, W means those kind of solution which is going to satisfy this. Okay, so suppose y1 and y2 is the solution of this equation. So if you check any combination alpha y1 plus a1 b1 or a2 b2 alpha or beta, if you consider alpha beta as a real, here I have considered a and b. Okay, so again that will form a vector space. Okay, now let us come to the main idea of the application of subspace. So one kind of notion, I hope that most of you are already aware about this concept. Okay, those who has done course on the modern control engineering, those who has taken this course as a open elective, so for them this concept might be new. Okay, so one concept is the idea of controllability and observability. Okay, so what is main theme of controllability? Suppose after mathematical modeling you come up with this particular system. So I am, for simplicity I am going to use this system, or you can also able to take this system. Okay, because this LTI system or LTV system, linear time varying system, is more simpler. Okay, so most of time first people are checking theory or developing theory for this system, and after that people are moving for this more complicated system like this. Okay, this is called nonlinear system. Okay, so here idea is, suppose I am going to develop some kind of machine and I have to control the behavior of machine. Okay, so first stage is that we have done the mathematical analysis of that system. Okay, and now what we are going to see, or what we are going to check, that suppose if I design some kind of control, then is it possible to move from one point to another point or not? Why I am telling so? Because most of time I have to control the state. Okay, and here x is the state. Controlling a state means I have to make sure that state will behave in some desired fashion. It might possible that I have to track some kind of trajectory like this. Okay, and I have some kind of system like this, x dot equal to u, where x belongs to R. I have just very simple system, and I have to make sure that after designing this u, x will track this particular trajectory and maintain this trajectory throughout the time interval. Okay, so that kind of requirement, that kind of problem is called tracking problem. Okay, so now question is that how to give guarantee that there exists a control such that I can able to maintain this trajectory. Okay, so one thing is that I can apply different control and then check it. Okay, so that is not basically consistent way to do that, because I have infinite many possibility to design control action such that I can force the system to behave in some specific manner. Okay, another way, using some kind of theory of linear algebra, I can give or generate some kind of conditions such that if I have system, so just checking some combination of these two matrices, I can give guarantee that there exists at least one control. Okay, sometime it might possible that control exists or not exist. Okay, so by checking through example or by checking through different combination, it is very difficult, very impossible, very inconsistent to tell that I can able to design control. So before designing the control, you have to check something. Okay, and that notion is called controllability. Okay, so controllability gives us one of the gateway such that I can give guarantee that there exists a control action or not. Similarly, observability. Okay, so what happens that whenever I have some kind of system, then in order to design some kind of feedback action, I need the information of state. Now, notion of observability is telling that how many minimum number of state if you measure. So using that minimum number of measurement, you can generate the whole number of state. Okay, so it means that suppose that I have to communicate with the whole batch. So I know that if I just communicate with the CR, then that information is transmitted to the whole class. Okay, so basically here if I just manipulate one variable, that is CR, then I can manipulate the whole class. Okay, so that kind of notion is called observability. But suppose that if CR is not honest, then what happens that if I am trying to manipulate the CR, I cannot able to manipulate the whole class. Okay, or if I am trying to give some kind of information that is not spread to the whole class. Okay, so if system is observable, it is possible to show that by the minimum number of sensor, okay, you are able to understand the behavior of whole state. Okay, so these two notions are very important whenever we are dealing with any system theory, okay, or control system design. Okay, so let us try to see this very simple example. Here I have current source, and here I have capacitor, here I have resistor. Okay, and here I have different, again similar kind of situation. So resistor, you can see that is the same, capacitor is C1 and C2. Okay, here I have one resistor. So it is possible to show that if you change U, then that change is not reflected on the X2, because I have this kind of closed connection, so current is not going to flow in this direction. Due to that reason, using this control, you cannot able to change the behavior, or this is called state. State means I have already told you some energy carrying element. Physically, that is energy carrying variable or element. So here capacitor is energy carrying variable. Here resistor is always dissipating. So there is no state which is responsible for the resistor. But here always I have some kind of memory element like capacitor. So one state is associated with this and this. It means that this whole system is second order system. Okay, so I can able to control x1, but I cannot control x2. So this system is called uncontrollable. So controllability, it means that whatever current you can apply, that is not going to transfer, that is not going to change the state of this system. Another notion of observability, suppose now whenever I am talking about observability, I am measure the output, and using output I am trying to see that is it possible to know the other state variable. You can see that here in this particular problem, if you measure y, then you are able to understand what is state here, state of this capacitor, but you are not able to measure x1 here, because x1 is function of this current, and due to that reason this system is unobservable. Means using measurement of y, I cannot able to give what is a specific measurement of this. Okay, and due to that reason I have written that this system, whatever system I have considered here, that is not controllable and not observable. Okay, so now let us try to see the general class of system, general class of linear system. So this is LTV system. Okay, and in the class of the vector space, I have already talked about this system x dot t, xt, b t, t u t. At that time I have talked that what different spaces are associated with this. You can able to generalize this to this class of system xt, and here at is now also function of time. Initially, whenever I am talking about LTI system, at that time I am assuming that a and b are no longer function of time, but here I am assuming that is function of the time. Okay, so now here I have again various possibility. I have matrix space associated with this AT, BT. Okay. Similarly, here each entry of matrix is changing with respect to time. Okay, so that is combination of functions and matrices. Okay, so now if you see the solution. Okay, so again in this class I am not going to solve it. Okay, if you are interested in solution, then already one lecture I have recorded and keep on the YouTube. You can see that solution of LPV system. Okay, and linear time varying LTV system. Okay, and this is called a state transition matrix. Okay, so a state transition matrix means if you know this, then you are able to understand what is x1, provided if you know all AT, BT and UT. Okay, now what is our aim? I have to define two things. Okay, so here in this particular lecture I am not going to concern about the observability. We know what is meaning of observability. We are going to focus on controllability, that control design is possible or not. Okay, and I have told you that main aim of control to manipulate the state. Okay, so let us try to see these two definition, that is called reachable subspace. Why subspace? Because it might possible I have some kind of LTV system. So x dot equal to AT xt plus BT into UT, and I am assuming x belongs to Rn, whatever requirement I have assumed. Okay, so now what I have to do, since I have to manipulate this state, so I have to make sure that is it possible to move from origin is always included. So is it possible to move from origin to somewhere, means if system is in rest, then it is possible to move from one point to another point. Okay, another way that I am going to check or do the reverse problem. Okay, I am trying to move from any other state to here. Okay, and due to that reason I have two different notion. This is called reachability. Okay, reachability means controllable from the origin, or this is controllable to the origin. Okay, so that is two variation of controllability basically. Okay, and I have to make sure that I can able to move from this state x t0 to xt in finite time. Due to that reason t0 and t1, so finite time interval. Okay, and obviously if you see this space, then this is a space of continuous function, because what I have told you that here x and x should be differentiable. And in the previous example we have already seen, at least if some vector that map from real to real, where field is real and this is real, and if this is continuous, then that form a subspace. Now I am going to see the general problem. Okay, general problem means now I have x and that is mapping from Rn to Rn. So this problem I am going to check. Okay, so component wise if you will see, then again similar kind of situation comes into picture. So I have some kind of space, n dimensional space, and where I have some way to define the continuity. Okay, so I have some kind of a space of continuous function consist all state x0 for there exists a input like this, and here I am assuming that I have multi input multi output system. So k dimensional is u is k dimensional. Okay, so if meaning of controllable from the origin means I have to make sure that xt0 to x1 xt equal to x1 I can go. Okay, and just you can substitute inside the solution. So if you put x0, then if something is controllable, it means that there exists some kind of solution for this particular equation. Okay, and this is integral equation. Okay, so we have to make sure that there exists a solution. Okay, similarly now if something is controllable to the origin, again I have to check that there exists a solution. Okay, now what I am going to do, I am going to see the connection between controllability and reachability. Okay, so it is possible to show for the continuous LTV system, linear time varying system, if something is controllable, then that is reachable too. Okay, and what you have to do, you have to just apply the reverse control. Okay, so same kind of things I have established using the mathematical expression. Please check it. That is very simple to check. Okay. Now let us come to the one example, and now I have what we have seen that if I have some space, so and whenever I am doing the mathematical modeling, at that time if my system is represented by LTV system, then I have inherent restriction. What inherent restriction? That state whatever I am going to consider, okay, I am going to consider those kind of state which is continuous. Okay, so I don't have all different kind of column vector. I have just restricted kind of column vector which follow the principle of continuity. Okay, so that will not whole space. That is some kind of subspace. Okay, now I am going to actually demonstrate the controllable and reachable subspace with the help of this simple example. So I have taken RC circuit, okay, two RC circuit where R1 and C1 and R2 and C2 I have taken different, okay, and I have some voltage U, okay, and after that I have come up with this state space model. I have applied the first principle. What is meaning of first principle? I know that if I current will follow through this, I1 current will follow through this resistor, then voltage V1 is R1 into I1. I know. Here, what I have assumed that voltage across this capacitor, that is basically a state. So when I have told you that physical interpretation of state, I have to just make sure that what kind of element that is going to carry the information or storing the information. So here I have resistor that is not going to store any information. Due to that reason, there is no state associated with these two resistors. But here I have two different capacitor. So I have two different state that is associated with capacitor C1 and C2. Okay, and that state is nothing but voltage. I have assumed. Okay, so if I know the voltage across this capacitor, then I know that charge Q1, that is C1 into X1, and from here I can able to calculate that current. This is current, that is I1, that is going to flow through this capacitor C1. Okay, so if I know what kind of current is flowing through this capacitor, I know the also same current will flow through this resistor. Okay, and now I can apply Kirchhoff's voltage law. This is very simple exercise. You might have done during your 10+2 also. So I have U, and after that what I have to do that, here I have R1 into I1, and after that I have here that is voltage. So I have I1 into R1, and this is X1, and after that I am going to substitute I1, and I1 is nothing but R1 C1 X1 dot and plus X1. Okay, and if you rearrange it, then what happens? X1 dot equal to, now I have X1 by R1 C1 and plus U by R1 C1. And same kind of things you can see here. I have written X1 dot equal to 1 by R1 C1 and plus, and here X is nothing but this X is X1 X2. Okay, so what happens? And there is no component of X2 is involved here. So similar kind of things here. Similarly, please drag for the second one. Okay, you can able to see that if you replace just by 2, then and R2C2 R2 to C2 comes into picture, then you are able to get the second expression. Okay, so I have second order system here now. Okay, and it is obvious because I have two energy carrying variable. Due to that reason, I have second order system. Okay, now what I am going to do, I am going to check that in this space, and actually one restriction that comes into picture, that a space contain the continuous function. Okay, so obviously that is some kind of subspace of the general space x1 and x2. Okay, and here x1 and x2 is function, some kind of function I have. Okay, so I have to generate that function. And how to do that? So for that I have to solve. In the previous class I have told you that whenever I have system like x dot equal to ax plus bu, at that time solution xt is nothing but xt0, and after that t0 to t, and here xt0 e power a t minus t0, x t0, t0 to t, and after that I have EA t minus tau b u tau into d tau. Okay, if you substitute everything here, this whole matrix is nothing but A and this whole is B. Okay, so I have taken here, means mathematical model of this system is LT linear time invariant system. There is no time varying component inside this matrix A and B. And if you solve it, then I have this kind of expression that comes into picture, and X has two states, that is x1 and x2, and both are the functions. Okay, continuous function I have. Okay, now what I have to do, that system is controllable or reachable or not. Okay, so for that we know from the definition is telling us that whenever something is controllable, okay, or reachable, at that time I can move from here to here. Okay, and actually controllability and reachability problem is inverse to each other. I have already told you that if something is controllable in continuous time system, that is also reachable. So there is no need to worry now. Okay, so reachable problem means I have x0 equal to 0, and after that this thing xt equal to xt1. Okay, so now you can see that in order to exist the solution of this, okay, and suppose if time constant of these two circuits are the same. Okay, so what I have assumed, I have different resistor and capacitor, and R1 and C1 is telling the time constant. Okay, so those who are knowing meaning of time constant, that is okay. Those who are not knowing, please do not worry. Okay, just you can see that R1 and C1 is appearing here. So I am going to keep the same number for R1, 1 by R1 into C1 and 1 by R2 into C2, that is omega. Okay, and if you do that, then this kind of mathematical expression comes into picture. Whenever I am talking about the reachability, at that time I have to reach from here to some non-zero state, and due to that reason I have to put this equal to 0. Okay, and if you keep this equal to 0, then I have this kind of situation that comes into picture. And here you can see that alpha where I have defined like this. So in order to transfer some system, okay, suppose I have to transfer in two-dimensional space, I have two different kind of things. There exists some kind of trajectory where everywhere x1 equal to x2. It might possible that everywhere x1 equal to x2. Okay, and another situation that x1 not equal to x2, because this is the space where x1 is in form of function, x2 also are in form of function. Okay, so you can see that in order to existence of solution, these two is 1 it means that I can only able to travel in those direction where both component is equal to equal. If that is not equal, I cannot travel using design of any control action. Okay, and due to that reason, what we are telling, that if time constant is the same, then I cannot able to span in whole space, but still I can span in some subspace. Why I am telling subspace? Now you can take the linear combination of these two. It is possible to show that you are going to live here only. Okay, so in this way we are able to find some kind of subspace inside the whole space. Now let us come to the controllable. So in controllability, just now you have to put that final state equal to 0. Again similar kind of restriction basically comes into picture. Okay, now it means that if you want to span in whole space, then you have to make sure that time constant of these two circuits that should be different. Okay, then only I can able to move in whole space and where each component is continuous, or whole subspace you can tell. Okay, so in this way we are able to identify that in which direction I can move or not move. Okay, so if something is not, suppose R1 by R1 C1 equal to 1 by R2 C2, it is possible to show that you can design any control action. Okay, but you cannot able to move those direction where both components not equal. Okay, that is the main thing. Okay, and due to that reason, notion of subspace you give us the visualization that where what part of system or what kind of space I can modify using the help of control. Okay, so some system is controllable, some system is not controllable. So somehow if you know the solution, you are able to understand that where I can move, where I cannot move. Second way, there are algebraic equivalence. I will talk sometime about the algebraic equivalence, that without solution how to give guarantee that I can able to move in anywhere inside that space. Okay, and some of you might aware that at that time we are checking this Kalman matrix B A B A square B and up to A n minus 1 into B, and we are just checking the rank of this. Okay, so once we are able to understood the notion of the basis and dimension, then we are able to understand that why we are just checking this rank of this matrix. So that is the story of the next part of this course. Okay, now let us try to check something more. Suppose M and N be the two subspace of same vector space. It is possible to show that their intersection is still a subspace, but union is not. Okay, and everywhere what I have to make sure that 0 will lie. So I have to show that since M and N is subspace of vector space, so obviously M and N contain the origin, and their intersection is obviously contain the origin. Okay, so these two requirement, so origin requirement is already fulfilled, and most of time origin requirement is violated. Okay, and after that obviously if you take any combination and intersection, then that will lie inside that. Due to that reason, intersection of two subspace is still a subspace, but union is not. Okay, so union of two subspace in a vector space is not necessarily a subspace. Sometimes it might possible, but not always. Okay, so for example, union of two non-collinear line through origin doesn't contain arbitrary sum of the element. You please check it. Okay, now it is possible to show that if you have two subset S and T of vector space, and I am going to denote S and T consisting all vector of form S and T. So we have given this kind of definition for sum of two set. Okay, so I have one set and this is another set. Okay, so I have two subset of same vector space, and after that if I will define addition like this, it is possible to show that let M and N be the subspace of vector space, their sum is a subspace. Okay, so in this way I can able to create some more subspace. Just I can identify one subspace, another space, and if I do this point-wise addition like this, you can see in figure I have shown that I have done some kind of point-wise addition kind of things. Then whatever this whatever this space comes into picture, again satisfy the property of subspace. Okay, so although union of two subspace is not a subspace, but if you define the addition in some specific way, then that is a subspace. And please check it, that is very easy to check. Okay, so two-dimensional Euclidean space, sum of two non-collinear line through the origin is entire space. The set of even continuous function and set of odd function are subspace of X of continuous function on real space. So these are the some example where if I will add like this, then I can able to find some more subspaces. Okay, so now it is time to conclude the today's lecture. So what we have seen in today's lecture, that if I have some bigger space, okay, which satisfy the property of the vector space, now I am going to identify some smaller space where same property, it means that I can able to define vector addition, I can able to scale out. Okay, and after doing that I can going to remains in the same space, means same subspace or same subset, then that space, that a smaller space is called the subspace. Okay, and most of time in problem subspace are involved. Okay, because if I have physical situation and I have taken the example of the linear time invariant or linear time varying system, okay, where it is possible to show that only in if I have physical constraint. Okay, and what is meaning of physical constraint? That we have seen that if time constant is equal, so that is physical constraint, then I can only move in some specific way. I cannot move in whole space. So we are able to understand now that there exists some kind of subset of the whole vector space where I can able to manipulate, I can able to perform same kind of operations such that all property of vector space remains the same. Okay, so with this remark, now this class is in from my side. If you have any specific question, then please let me know. If you don't have question, then I am going to end the today's lecture. Thank you very much.